CNT125, we're continuing our Chapter 7. We're now on the section on switch path management. I'll get it yet. We just talked to some switches, switch port security type of thing. Now we're going to look at switch path management. Now, redundancy is always a good thing. If we have a failure in one route, our devices can hopefully send data on the other route. The only problem we have with switches is if a switch has more than one path to send data through, it's not quite intelligent enough to do the load balancing thing, sending some this way, some that way. It can't quite do that. So we could, if we have redundant path on switches, we could have a broadcast storm where it really just starts looping the data through the network. So there needs to be something in place to kind of stop the redundant paths, but make sure they're available in case they're needed. That comes from something called STP, Spanning Tree Protocol. Spanning Tree Protocol was IEEE 802.1d standard that would prevent these loops in the network, but allow things to adjust if needed. So it would artificially block the backup path, but if the main path broke, then this one can open up and let traffic through. So STP can adapt to changes in our network and actually prevent these loops, but also allow traffic through in case a failure occurs. So what it would do if you have a switch network like so, if I had two paths over here, the switch would be like, it could potentially start looping traffic through the network. So what STP will do is artificially block this and leave this pathway open for everybody, if you will. So it does that by selecting a root bridge, basically, kind of like the switch in charge. And it does that by looking at a priority field MAC address combination. The lowest MAC becomes the root bridge by default, and then it's the one that figures out the least path and kind of puts the other paths in a blocking state, if you will. It'll disable those links that are not part of that shortest path. And it does this kind of thing right here, where it kind of blocks this shortest path, if you will, or this redundant path. So that is going to hopefully prevent your bridging your switching loops, if you will. Now, the STP, it communicates back and forth with these bridge protocol data units, BPDUs, and it can set these switch ports in any of these states: blocking, listening, learning, forwarding, disabled. First thing here, blocking, this redundant path, it'll put it in a blocking state. No traffic is going to go in or out. With our listening state, it's going to listen for connection and see if it needs to. It's not going to forward any traffic. It's going to listen to see, am I needed on this pathway, if you will. Learning whether there is a better path. Forwarding, actually the state this port is open and it's moving data through. Or disabled. Maybe I do a whole no shutdown or a shutdown on this, or a network management station shuts it down. So those port states could be in effect. But they're all part of the bigger picture of finding the shortest path and blocking the redundant, or the path that's not the shortest, if you will. The redundant path, if you will, STP. There is newer technologies to replace STP, Rapid Spanning Tree Protocol, Trill, SPB, so forth. And there's even a rapid per VLAN Spanning Tree Protocol Plus. For these, familiarity is the key right now. As you start seeing traffic move through a network, or start seeing protocols move through a network, and you start seeing these, you'll understand what is happening. And this, for the most part, on line networks, this is just happening for you. You might manage this in some networks, but in some networks it's up and running and it's taking care of this for you. As we move on to the next section on hierarchical design, Cisco and a lot of manufacturers have developed a hierarchical design for switches or networks, three-tiered architecture, where you have the access layer, distribution layer, core layer kind of thing. And a lot of devices that you would buy are based on that part of the network, that layer of the network, if you will. Your access layers, where your devices connect in, your desktops, your phones, your printers, your access points, those sorts of things. These would typically be layer 2 switches. Your distribution layer, this is the high bandwidth connection between those switches. These might actually be like layer 3 switches. Actually doing some of the basic routing, and I'm putting little air quotes around this, basic routing, moving data between those switches. And then I might have core layer that's moving maybe from one whole building to another whole building, one whole campus to another whole campus, if you will. And then there would be a high path connection out to internet and or maybe other sites kind of thing. Another way to look at that would be like so. If I look at kind of like aerially, if you will. This might be different parts of my building. This might be different wings or different floors of my building for that matter too. So my devices are designed, a lot of devices are built for a certain function in this network. So you might actually see access switches, distribution switches, core routers kind of thing. And that's giving you a clue as to where these devices are designed to be in my network. The advantage of this is for traffic flow, where we can control and minimize the amount of unnecessary traffic. If this traffic is only for this part of the network, these switches will contain it and keep it here and not move it to another building or another floor of the building or of the facility. And that's being accomplished by some intelligence up here at the next layer. They also talk about an east-west traffic, north-south traffic. The east-west is within peers within kind of like that layer of that network segment. So here, this would be east-west traffic, layer, traffic from here over to here kind of thing, or even from traffic from here over to here, if you will, at this peer layer, if you will, okay, or even this switch here over to this switch over here. Your north-south is I'm now trying to maybe reach a destination outside my company. So now I'm talking about traffic that's working its way up through the layers and potentially even out to another branch office or the internet. That would be your north-south traffic. And that's actually a little easier to see here, if you will. North going this way and out. Okay. So you'll hear the terms east-west and north-south, and just recognize whether it's like kind of in my building in that layer, if you will, or leaving my building going out through upper layer equipment. And that's what they're showing you here. Between your peers, east-west, and actually leaving your facility, maybe heading out to another site or even another, or out to the internet kind of thing. A newer hierarchy design was your spine and leaf architecture because of adding in virtualization, other things like that. So some of your network architectures look more like this now, where I have my switches here and my high availability, like layer 3s up here, and then my internet connection out here, if you will. So you might actually see that type of arrangement, or you might see this type, I'll show you this way, this type of arrangement here with your equipment. This is actually showing a little bit more of the details of how the equipment's hooked up. So they talk about top of rack switching or end of row switching. So if I look at a data closet like so, or maybe this is a series of data closets where all the devices in area connect to this switch up to here, I might have switches at the top of the racks all connected together. Actually, I think I have one here. This will be right here. All these racks in my building are connected maybe to a layer 3 switch, but all my switches are up here. Versus an end of rack where I might have all the switches and everything down to basically out here. My device is here and all the switching is occurring at the end of the row with maybe a higher bandwidth switch for all of them. So this might be getting into some of the physical arrangement of our equipment and how we're moving our data around to accommodate this. Okay, so you might hear these terms as well. Top of rack or end of row switching, if you will. With my spine and leaf, I get a whole bunch of these advantages: redundancy, scalability, latency, performance, security, expense, etc. All those types of things. That brings us to availability. The term availability is just that. How consistently are we able to access our resources, whether it be data on a server or the web pages, that sort of thing. This is usually represented as a percentage and the number of nines. Sometimes they actually talk about the number of nines. A 99.5 versus a 99.9. And actually, I think I have a breakdown here showing you a couple of these ideas. If I have 99% availability in my network, by the end of the year, I might have 87 hours of downtime. well, 87 hours, that's like almost 2 work weeks. So when we say 99.9 or 90.99, we're getting at a better availability network. 99.9 is basically like 1 day of not available. 99.99 is basically like an hour of unavailable network time within a year. So a lot of places will talk about their availability as the number of nines they have, a 4.9 or a 5.9 shop kind of thing. Uptime is a measure of how available something is or how long it's been up and operating. I can actually see this in a Microsoft Utility Task Manager type of thing. I can also see this if I run commands at Linux or Unix uptime. It'll show you how many days, weeks, months, etc. These are some terms that hopefully you might remember from 120. I'm bringing them back as just in case. Fault tolerance is the capacity to live through a fault or live through unexpected events. A fault might be an error that occurs, and a failure might be because of that. So I might have a piece of equipment break, and it would cause maybe a failure in a system. So fault and failure are terms that kind of go together, but a fault might be the reason for a failure. If I have let's say a keyboard fail on my computer, it should not affect other things. That is still a fault. But if I have, maybe the power supply on a switch fail, well, that was the fault. The power supply failed on the switch, but the failure is it brought down a whole part of the network because of that fault. So something being fault tolerant, we're trying to prevent faults from progressing to failure. So, if I have a switch with redundant power supplies, if one power supply fails, that's still an issue, but it didn't bring the whole switch down or that whole part of the building down. It takes planning to do that, though, and usually some money and budget to do that, to have equipment that has some of those things built in that I don't have those problems. Adding things like redundant links helps with this as well. I might have, instead of just one link between two switches, I might have 2 links in case one of those were to fail. Maybe the cable breaks, maybe a connector breaks, maybe something gets unplugged. The other one is still there and functioning. That would be my port aggregation, if you will, or NIC teaming. In this, I have some fault tolerance, I have some additional throughput, but I also have the potential of load balancing, where I might actually have more bandwidth, but the big issue is if one of those links were to fail, the other one's already there running, and I don't lose my connection. This is actually something we do in our cabling class. I have people do this in our cabling class. We link 2 of the switches together. We configure them to work together, and we start unplugging them one at a time and watching what happens in our network. And it really is just a little bit of configuration. I think I have a sample down here of doing that. And I'm taking those 2 ports and making them act together, called link aggregation, to do this. And right here, I think, here we go. Here's the configuration we do. We take the port and we kind of group it together. We group those 2 ports together, act as one. So if one of these links, I think they're showing 3 here, but if one of these links were to go out, the other one's already there running, or in this case, the other 2 are already running. That helps with our overall availability. And with that, I might have the ability to do some load balancing, where it's literally running data across both of those links, maybe giving us more throughput, but giving us one is not running at full capacity all the time then. So in a server environment, I might actually have two servers clustered together, and this device out here makes it appear to the internet that there's one server back there, but it literally is using both of the servers, or having one as a redundant, if you will. Many cases, it'll, a popular website might have multiple servers back there handling the traffic, and they're basically redundant copies of each other, and just handling all that traffic. The web client looks like a single web server. On the back end, that load balancer is directing traffic even between the 2. The clients aren't aware that it's going on. Clients aren't aware there's two or more machines back there. As far as the clients are concerned, it looks like one server, but those 2 servers are doing the work. They're kind of working together. Alrighty, that's our next switch section. When we come back, we'll start talking virtualization.